Good afternoon and good evening, friends and colleagues. Welcome to this interdisciplinary webinar. Now, this online event is co-organized by the Center for Water Technology and Policy at the University of Hong Kong and the Water Supplies Department of the Hong Kong SAR government. My name is Frederick Lee, and I'm the Executive Director of the Water Center. Now, the Water Center is an interfaculty collaboration between the Faculty of Engineering and the Faculty of Social Sciences at the University of Hong Kong, okay? And you can actually see the logo of the center right above my head, okay? And we are now seated in the Social Science Chamber of the Faculty of Social Sciences, okay? Now, since the Water Center was established 2 years ago, we have been working closely with the Water Supplies Department on several salient policy issues in Hong Kong's urban water sector, okay? And today, we're going to focus on one salient policy issue, water losses in a city's water supply system. And we're very pleased to have two leading experts, okay? One based in the United Kingdom and the other based in the US, Mr. Malcolm Farley, based in the UK, and Mr. George Kunkel, based in the US. And they're going to share with us their experiences, their insights on this problem, and how this problem has been defined and tackled, okay, in the United Kingdom and in the United States. Now, after the two speakers delivered a 20-minute presentation, then two discussants, okay, will present their observations on how this problem has been addressed, okay, in Hong Kong, and try to make a connection between the local and the international. Specifically, they will address the question, to what extent and how Hong Kong could learn from the experiences of the United States and United Kingdom, addressing this problem of water losses in urban water systems. Now, friends and colleagues, you can submit your questions through the webinar platform. And then at the Q&A session, I will direct your questions to particular individual, particular speakers or discussants at the Q&A session, okay? Without further ado, let me introduce the first speaker, okay? The first speaker for this webinar is Mr. Malcolm Farley. Mr. Farley is a chartered engineer, a chartered environmentalist, and a chartered water and environment manager. Malcolm has more than 50 years of experience working with water utilities around the world. He has served as a consultant for many international organizations, including the Asian Development Bank, the World Bank, USAID, and the World Health Organization. Malcolm specializes in managing non-vacuum water and leakage reduction strategies. He has also conducted water audits and training workshops for water utilities around the world. Mr. Farley is a fellow of the Chartered Institution of Water and Environmental Management. In 2012, Malcolm was made a fellow of the International Water Association in recognition of his contributions to the association. Mr. Farley is a co-author of a book entitled Losses in Water Distribution Networks, a practitioner's guide to assessment, monitoring, and control. Mr. Farley, please.
Thank you very much, Frederick, for that very nice introduction. I'll just share my screen and then I'll make my introduction. Well, good morning, everybody. Good morning for me, good evening for you. I'd just like to say I'm very pleased to be here this morning, and thank you, Frederick, for that introduction. I'm going to talk today about the UK's capability for managing leakage, policy goals and technological innovations. Now, I think you have circulated earlier a lot of background information on the UK water system, background data explaining the structure of the UK water industry and the targets that our water companies are expected to achieve. So that's the focus of the talk today. The key points I want to try and understand and discuss during the little presentation is how is the UK water industry assessing its leakage targets and addressing them? How can it reach those targets? And we've talked earlier today about, I saw from the earlier presentation, is it possible to ever achieve zero leakage? It may be possible to get right down to very low levels of leakage, but can we achieve zero leakage? And there are initiatives going on now in the UK industry and by the UK Water Research Limited to look at the ways in which we need to address leakage to get it down even further. And it's called assessing zero leakage. So the UK water situation in terms of leakage is still quite high compared with many countries. We don't use percentage as a key performance indicator. We use a volumetric measure in megalitres of water lost per day. And so the targets as set by the regulators reflect the amount of water that those water companies should reduce their leakage by in terms of megalitres per day. So every water company is now set a target. But that wasn't always the case. You'll see from the graph here that back in 1994, 95, water leakage was 5,000 megalitres per day. And it started coming down just after that over the next few years when the regulators became more severe and linked the loss of water with bad management of the water company. Because I think we all agree that non-revenue water is an indicator of a water company's operational efficiency. So the water company and regulators were attempting over the next 20 years to get their leakage down. But as you can see, it reached about 3,000 megalitres per day in 2000, something or about there. And for the next 20 years, it was flatlining. The leakage, the companies became very, very sort of laid back about leakage in their companies. They thought they'd reached the economic level of leakage and they didn't try to achieve it any further. Until around about 2018, 2019, when the regulator said, this is not good enough. We're going to have to get really stringent targets now with climate change, the publicity that the companies are getting. The customers are saying, if the water companies are losing so much water, why should the customers try to save water? And so they started setting quite rigorous targets. Those targets were based, as I've said, on a reduction from the present level to a lower level. And every water company had a different target because of the different formulations. Now, some of the water companies performed better than others. And in 2017 and 18, 9 of the 20 companies in England and Wales missed their leakage targets. And when they miss their leakage targets, the Ofwat, the regulator, can put stringent fines on them or prevent them from investing further and prevent them from charging customers more for water. So they're quite sort of hard targets. Thames Water, the biggest water company that we have in the UK, with the biggest population to serve, was the worst offender. You might say they have much more difficulties of getting leakage down because they have a mixture of very urban situations and very rural situations in their water company area. But they were fined a massive £120 million by the regulator for failing to manage leaks adequately. And in fact, even worse than that, the company chief executive officer was asked to resign because he was found guilty of not meeting targets, the company not meeting targets. So there are quite stringent punishments and fines for not reaching our targets now. So because of this incentive and the incentives of fines and punishments, all the water companies now have said, well, we will get at least a 15% reduction over the next asset management plan period, which is the next 5-year period of the water company operations. So that goes from 2020 to 2025. So all companies are proposing at least a 15% reduction, and some of them are going much further. 17%, 18%, and 1 or 2 are saying reductions of 25%. Now they have to reach these targets, otherwise they will get penalised again in terms of fines. So they are, once they've set a target, they have to reach them. And of course, a lot of the targets now have been sort of set back by the COVID pandemic. People can't, for the last 6 months, haven't been able to be as efficient in managing leakage, leak repairs, or leak location than they would have in the past. But the regulator is not taking any notice of that. They have to still reach these targets. To reach the targets, of course, the operators will have to make very strong operational responses and some infrastructure responses as well. Investment in new pipe work, in new fittings, and a lot of technology is needed to meet these new targets. And one of the key technologies, or rather the key factors in reaching targets, is innovation. And innovation is very much a key issue now in the United Kingdom for trying to find improved ways of finding, fixing, and reducing leakage. Fixing leakage in particular is important, as we will see later on in the presentation. So innovative ways of finding, fixing, and reducing leakage for the next generation of leakage management tools. And by that I mean, first of all, we need better sensors, or more widely spread sensors, to cover the network and in terms of monitoring and recording where the leaks are. Better data communication from these sensors, and we have sensors not just for leakage, but all sorts of sensors for metering and for monitoring water in different aspects. Communication analysis systems. We've all heard of big data. The amount of data that's coming in from these sensors now needs more software, better analysis technology using IoT, AI, machine learning. All of those will help the operators to understand and analyze and manage the data that they're getting, so they're always operating in the right area for the best efficiency. Alongside that, we need to get better leak detection technologies, more advanced detection technologies. We've emphasized for so long now acoustic technology. There are other ways of finding leaks or of finding data from leakage and managing it. So we need to look at those other technologies besides acoustic. And repair is one of the major angles of making leakage targets, get them reached quickly and making them sustainable, because we know that the longer a leak runs, the longer it can produce volumes of water that have been lost. And the gap between finding a leak and repairing the leak is quite crucial. And they have to be done efficiently. So really now the steps in a leakage reduction strategy all angle around smart networks. And we all talk about our smart networks, but what is a smart network? I think to be truly smart, a network has to have all of the components of the operational network. It has to be able to accurately quantify leakage, so it has to have to be good metering and good understanding of data and communication coming in. So quantifying it, then locate the leaks as fast as possible. And these need to be located accurately. We need to find out where the leaks are and make sure that we are always working in the right place. Repairs have to be done quickly, as I've just said, otherwise the longer they're left, the greater the volume of leakage. And I think this is where, certainly in the UK, we've fallen down in the past, the gap between locating the leaks and then repairing them. So we need to fix that. And calm networks now, we're looking even more and more at reducing pressure in the network, to squeeze down the pressure and by monitoring pressure and keeping it down to the optimum level. But also now we're finding that transients can cause more of a problem than we first thought. Little changes in pressure or sudden changes in pressure can create transients, which create a hydraulic ram, which can help to break the pipes. So we need to monitor and eliminate transients in the network. Background losses. These are something that's always been considered as difficult to eliminate, because they've always been the small leaks, little weeping joints and drips from taps. Always the ones that are difficult to find and fix, and probably not economic individually. But now I think we're getting to a mindset where, because of these stringent leakage targets, all of these losses have to be brought down. They can't just leave the background losses and just take off the bursts and the big leaks. And probably one of the most the biggest things we can do for achieving zero leakage is to make sure when we lay new pipes and new networks that they're leak free. So this involves monitoring the contractor, monitoring, supervising the quality of repairs, quality of installations, quality of materials. So all of those together are the components of what we need to put in place for a smart network. And in the UK, we have, as in many countries, in all countries have challenges, but we tend to have a lot of old pipe work, aging network with a low replacement policy. It would take hundreds of years to replace all the pipes in our country at this replacement rate. We also have an aging workforce, and aging workforces means people retire, they take all the knowledge with them and the skills and expertise, and it's often not replaced. It should be replaced by young people coming up and taking over these posts, these operational posts. But there's a lot of apathy, I think, amongst Generation Z in the UK, except nobody wants to go out and find leaks with a listening stick anymore. That's old hat, traditional technology. And I think there is a lot now to interest young engineers, young people coming into the business in terms of technology, software, all the things that young people can do better than older people, the networking and finding out, analyzing data from the sky, from the cloud and things like that. So I think there is now a scope to bring in a different generation of skills into the water industry, needing to cope with this new technology. We have problems with climate in the UK. We have contrasting cold and hot climates, particularly now with climate change making its effect. We have cold winters where pipes freeze and then they thaw, so we get burst followed by that. And then we have hot summers where we have droughts and people want to use more water than is available. So sometimes we have to restrict the water supplies. At the same time, through all this, we have to keep customers happy and make sure that customers can get sufficient water for their needs. And we have to ensure that customers are not complaining, because that's another performance indicator by the regulators: customer satisfaction, customer complaints. And over the last 6 months or so, we've seen a change in demand patterns because of COVID-19 pandemic. We've seen more people working from home, offices closing, so less water being consumed by the commercial customers, but more water being consumed by the domestic people at home. So that's flattened out the demand in a way. That's lowered the peaks, and so water companies have to take into account this when they're producing their water. Drivers for the industry now, we've got, as you've seen from the targets that have been set, they have some very robust regulators. We have Ofwat, which is the economic regulator, which controls the pricing for the customers, ensures the customers are being treated fairly. And we have and of course, responsible for leakage. Then we have the Environment Agency, which is a water quality regulator. So they're responsible for not just quality, but quantity taken from the country's rivers and reservoirs. So they're responsible for water volume and volumes taken, keeping the environment safe and healthy. We've heard about stringent targets and the incentives that the water companies have now. They've all agreed to meet these targets over the next 5 years. And if they don't, there are not necessarily incentives, but there are some incentives, but mostly they're price restrictions and their fines on the companies. But some incentives which are interesting are that Ofwat is now supporting an innovation fund. It's actually encouraging companies to meet with suppliers and cooperate with suppliers and people who manufacture technology to actually innovate and reduce some of these, or rather increase some of the technology that can reduce the leakage. There's also, of course, media attention and public relations. the media are very fast to pick up on large amounts of losses from water companies, and the customers as well are quick to point out that if the water company is leaking large amounts of water, they can't really shout at the customers to reduce their consumption. And because the water companies are all privatized, some of them by international holders, international companies, they have to maintain dividends. So they have to be successful. They have to produce income, and they have to produce dividends for the shareholders. And we have a lot of political pressure on the water companies now. We have politics of leakage, politics from the public relations about how water company bosses are getting far too much income. And there has been talk until the last election about renationalising the UK water company, about putting it back into the public arena. That hasn't happened now because a different kind of government is now in charge. So the steps we have towards getting down to these targets, even if it's not zero leakage, it's the steps towards minimizing leakage down to squeezing the economic level of leakage down below that to eliminating as much leakage as possible. And I think there are four main steps in this aim. There's prevention, awareness, location, and repair. And prevention means, as we've said, as we've seen earlier, let's have any leaks on new pipework. Let's make sure the pipework is all leak-free when it's laid, so it remains free of leaks throughout its economic life. And that's just a matter of controlling the contractors and the pipe laying. Minimize the leaks on the existing network. This is the awareness again coming in. When all new leaks are found, they have to be quickly repaired, and repairs have to be quick and economic with minimum disruption. Background leakage is eliminated, and then we can confidently, by metering, we know that from using our smart meters, we know when we've achieved success from doing all of these operations. So these are the four new pillars, I think, of leakage control, along with the existing pillars of active leakage control, pressure control, repairs, and infrastructure management. So these go side by side with active leakage control. In 2020, the UK water industry has made some progress. It's reduced by 7%. You saw that graph at the beginning of the presentation where leakage was over 3,000 megalitres per day. It's come down a little bit from that now by 7%. Customer use has fallen very slightly, but this is probably due to not more being done because of COVID. So that's come from 143 litres a day to 142 litres. Still not good enough because many countries do have much lower levels of that. They can squeeze it down to much smaller volumes. And the overall volume of water we've seen now has fallen. It's down to below that 3,000 megalitres per day that we saw on the first graph. Some highlights from the various water companies. All of the UK water companies are now practicing some kind of innovation. And I think an example of this is one of them, Affinity Water. This is a water company covering the west of London. That's shown a 15% reduction in leakage already in the last year through using network coverage of monitoring sensors, monitoring the noise from leaks. So the more of these you have in the system, the more immediate the understanding of leakage is, and you can deal with it more quickly. A lot of these data loggers are now correlating loggers, so you can not only identify where in the network a leak is by remotely, but you can also correlate between it and find the position of it. And some water companies like Angling Water are using other kinds of leak detection equipment like thermal imaging drones to detect leaks, to find and pinpoint leaks. So getting away from acoustic methodologies, which involve a lot of work on the ground. SES Water, another sort of West London water company, Southwest London, has partnered with Vodafone to create an intelligent water distribution network. Northumbrian Water, using satellite technology, not just drones now, we've got drones, satellites, we've got infrared technology. Yorkshire Water is now famous for piloting the UK's largest smart water network, taking into account all of those components of a smart network that I was talking about earlier. And although it's a traditional technology, it's not all that innovative. United Utilities, which have a lot, it's one of our northwest water companies, big water company in the northwest. A lot of big trunk mains, big transmission mains, which are notoriously difficult to find. They're using sniffer dogs to detect leaks by smell in the transmission mains, and this is maybe a traditional technology that works well in certain cases. So we should be embracing all technologies. So just having a look at those key points again. How is the UK Water Industry addressing its leakage targets? Well, I think we've found that it's doing that by innovation, by hard work, by new technologies, by integrating the components of a smart network into its operational practices. Can we ever achieve zero leakage? Probably not. But I think what we can do is use all of the technology, all of the innovation to our knowledge, and all of the good practices that we know are out there to achieve almost zero leakage. So we'll see. In 5 years' time, I may be able to come back and tell you how the water companies achieved their targets. For now, thank you very much.
Okay, well, thank you very much, Malcolm, for your very interesting presentation. There's a lot of information that you have shared with us in regard to how water utilities in the UK have tackled this problem. We are now going to take a 1-minute break. So anyone in the audience want to take a bathroom break, you can do it now. Okay, 1-minute break. Yeah. So let's switch to George. Can you switch to George? So George, yeah. George, are you getting ready?
Yes.
Okay. I'm going to introduce you in about like 30 seconds. So to make sure that you're ready, yeah. Have you lost George? Malcolm, we seems to have lost George. George is back. Oh, okay. Hold on a second.
Hello, this is George Kunkel. Can you hear me?
Yes, George, you are back. Good to
Very
have you.
good.
So can you show your face, first of all?
Now I can.
Okay, good, you're back. Okay, so, yeah, so are you getting ready?
Yes, I
I'm
will
going
share
to- I'm
my
going to-
screen.
Yeah, I'm going to, first of all, I'm going to introduce you first. So give me 1 minute
Very
to
good.
give a brief introduction to the audience. Yeah. Now, we are very pleased to have our second speaker on the screen with us now, Mr. George Kunkel. Okay, so George, I'm going to give a 1 minute introduction, okay, about your experience to the audience here. Mr. George Kunkel is principal of Kunkel Water Efficiency Consulting. Okay, George has more than 40 years experience consulting with water utilities, manufacturers, and research organizations. And he has led the water loss control program in Philadelphia for 20 years. Now, currently, George is serving as a Public Service Institute instructor with the Pennsylvania State Department of Environmental Protection, providing training and water audit services for water utilities in the state of Pennsylvania. Okay. Mr. Kunkel is currently the chairman of a subcommittee under the American Water Works Association that publishes the famous manual, M36, Guidance Manual on Water Audits and Loss Control Programs. And he's also a co-author of the AWWA Free Water Audit software. Yeah. In 2010, George was the recipient of the Water Star Award from the Alliance for Water Efficiency. In 2016, he received the AWWA's Peak Performance Award. So I'm very pleased to introduce to you Mr. George Kunkel. Okay, George, you may start your presentation.
Very good. Very good. Good evening to everyone there. Thank you, Frederick, and thank you to all the organizers, and thank you to everyone listening in. I'm very appreciative that you're joining us now, and I'd like to give you an update on the status of non-revenue water management in the United States and all of North America. I will note that the situation is quite a bit different than the situation in the United Kingdom, as Malcolm just described. In the United Kingdom, you have several dozen large water companies that provide water service. In the United States, it's much more fragmented, over 50,000 systems, large and small, and even the regulatory environment is very fragmented. Non-revenue water is not regulated per se at the national level. It falls to state and regional levels. So there are several hundred regulatory agencies involved. So quite a bit different. In your background slides, you were able to review my involvement and developments over the past 30 years. Much has occurred since then. I'm very proud of the amount of work that's been done, research and tools, but this presentation is going to talk about where we are now and perhaps even in the past year. Now, within the United States, the main focus at this point is on data collection. The United States water industry is still relatively early in this journey and not nearly as far along as the United Kingdom. We are at a point, however, where we're focused on gathering data, and many water systems are now required to submit a standardized water audit. So as we look at that data, we're looking at volumes of water supplied, volumes of water consumed, and therefore volumes of non-revenue water, or perhaps the difference. How do we assess that? What are the best indicators used now to analyze that data? A very recent development through the American Water Works Association has been an updated policy on the use of performance indicators for non-revenue water management. The most fundamental development in that is that AWWA, the American Water Works Association, now regards performance or percentage performance indicators as inappropriate for use. And we liken it to the quotation that you see on top, that for every complex problem, such as non-revenue water management, there is an answer that seems to be clear and simple, yet it's the wrong way to approach it. And this is emblematic of percentages which have been in use because many believe that they're simple to employ and track, and they're straightforward, and you only have one indicator, one number to follow. We feel that, well, for one, you don't need to rely on a single one. In fact, it's probably a weak practice to rely on just a single indicator. And two, we need an array of indicators that are robust and reliable. So let's look for a moment at the percentage indicator. And this is a volumetric percentage, which you can see shown in this graphic. I've got a chart here showing water supply volumes year by year for a given water system. In the blue, how much consumption has occurred through the billings year by year. And there's always a difference. That difference we know is the non-revenue water here in the black. Let's imagine at a given point in time, a system may find one of its largest industrial customers has closed. So a large water user is now not using water any longer. You'll see the dramatic shift downward, both in the water supplied, the water consumed. If you're measuring by percentage, as we see on the right side, you're going to see a large jump in the percentage that this non-revenue water volume or water loss volume is. Even though, as you see by volume, that water loss volume continues to decline. So in an unusual, I'll admit, an extreme example such as this, the percentage indicator can actually give you an opposite effect than what is occurring in the system, suggesting that losses are increasing when in fact they're decreasing. In January of 2020, AWWA published the committee report from its Water Loss Control Committee that again recommends against the use of percentage indicators of any kind. And it has offered two new indicators, the loss cost rate, which we feel will be a very important indicator, and then a secondary indicator, the water losses rate. And I'll touch on each of those. So we in the United States, we're at a point we have considerable data that's now been gathered in a number of states, particularly states of California, Georgia and California. So I've put together a chart here of some data, and this shows the loss cost rate. And we have a version of this indicator that measures both the apparent loss or the commercial losses and the real leakage losses, the physical losses. We're looking at the real leakage loss rate here. Now, the loss cost rate is really just a combination of two functions. It's looking at the value. It is expressed in value per service connection per year. So it's marrying the rate of loss in gallons per connection per day and converting that loss volume into a cost. So we have, in this case, across these two states, we can see a wide range of values, some very high, some very low. When you get to the high end, these are systems that have either high rates of leakage or a very high cost of water, or probably a combination of both. The value of this indicator is that it reveals both, that it does reveal a cost impact. So we think that's going to be very important. It has good public relations effect because when you're thinking of a per connection, the public will think in terms of per customer. We feel it's good to identify these systems that are really at the outer bounds of a data set that are really struggling. We don't feel that it's necessarily that this will be used for target setting, however. Okay. And just to mention on target setting, This graphic, known as the 4 pillars graphic, may be familiar to a number of you, and it attempts to show visually how to approach a target setting process, in this case, again, for real losses. And the concept of the economic level of loss has been traditionally taken as what might be the goal for many water utilities, although Malcolm is now suggesting the UK is going well below that, maybe toward a goal of zero leakage. But for now, let's assume in a given year you have a volume of leakage shown by this outer box. If you strive to reduce that, there's a point that is economic where the amount of money you spend on your loss leakage interventions equals the amount of recovered funds. There is, in theory, a technically low level that could be calculated. And how we would strive to attain these 4 different arrows. We have active leakage control, leak detection, and district metered areas. We can use pressure management to perhaps reduce loss. We can optimize the repair functions, and we can focus on renewal of the system. And all these would drive leakage down. This approach, especially perhaps trying to define the economic level, would be appropriate for Hong Kong. This approach can be data intensive because it does rely on having accurate and consistent cost data, as well as good measures of leakage. For many systems in the United States, this is still a reach because, again, most systems are early in the data collection realm. They have not quantified their leakage adequately, and in many cases have not quantified their costs just yet. So that's why in the United States right now, we might focus instead on those systems that are the outliers. So again, if I look at this chart and look at these systems that are out here on the far edge of the chart, showing high leakage or high cost of water, perhaps keying on those initially would be better over the next several years. We're looking at identifying, getting the data to identify what are representative percentiles of these performance indicators. So this line right here represents the 90th percentile. So 10% of the systems fall in this extreme range on this graphic. And definitely we feel it would be economic, at least for those systems, to bring down their losses at least toward the 90th or eventually toward the median or 50th percentile basis. The other indicator that the Water Loss Control Committee has recommended is looking at total losses, real and apparent, placing them on a unit basis and the volume per service connection per day. We have been looking at individually real losses and apparent and volume per connection per day. We feel it's good to look at the total of those two, the sum, and that's a good high-level indicator just for trending year by year. If we see a change in a given system and their real or apparent loss, we also want to note what is the total loss volume doing. And this assists in the validation of the data, since again, we're still early on in the data collection phase. We don't feel that this is necessarily an indicator that we're going to use in a standalone fashion. Again, we want to use it in looking at real and apparent losses too. And we don't feel this is one we want to use it for target setting. So those are the two new indicators. But on a higher level, rather than just focusing on percentages, we feel we have an array of indicators, and you could classify them under the 3 V's by focusing on the volume of losses. And we have an array of indicators we can look at that are volumetrically based, looking at the value or the cost. And now we still have indicators that key on value. And finally, on the validity of the data. And actually built into the water auditing process and AWWA's free water audit software, there is a mechanism to grade or rate the trustworthiness or the validity of each of the input components, and thereby get a composite score on your water audit. on the rating or grading of the data quality. Again, we are early with many systems. Data is crude for many systems. We need to distinguish those systems that are early in their process with less valid data, and hopefully can have them move up the scale over time and improve their data quality. So for the United States right now, validity of data is also a parameter that we want to track, and we have indicators for grading and a total composite score to do that. In our committee report, we've got a table that lists the variety of performance indicators now that exists, their description of their use and suitable purposes. For the purposes of this brief overview, I just want to highlight that, again, you can see that there are indicators that exist based on volume. There are indicators that exist based on value or cost. And we do have indicators or primary indicator around the validity of data. So looking at this suite of indicators, we feel that we have the capability with water systems to assess their non-revenue water in a very comprehensive way, and that is superior to just using a single percentage. Now, I realize percentages are still in use by many systems in the United States and around the world, and I believe that Hong Kong also uses a percentage. That's fine, that could continue. What I would urge Hong Kong and other users of percentages is, in addition to the percentage, consider starting to track or trend some of these additional parameters too, and look at them in comparison. And you see how they trend over time, and see if some of these other indicators might also you'll find useful for your operation, and you may be able to use them in specific manners. For instance, leakage control. Just to highlight some of the developments in the United States, and especially around data collection. And again, in the United States, we don't have national regulations on non-revenue water. So it is occurring at the state and regional level. The two most prominent states are California and Georgia. They've enacted legislation that require annual water audits to be collected using the AWWA free water audit software. They have several years of data now, and they've been doing analysis to look at the trends. I'll note in California, they will be the first state that is moving toward a process of actually setting some targeting of loss reduction. So whereas in the United Kingdom, they've had leakage targets for many years, starting next year will be the first year that California begins to phase in some types of leakage targets, and that will be the first state in the United States to do so. At a system level, I'll highlight two water systems, one in the United States and one in Canada, at the opposite ends of the continent. On the Pacific Ocean, we have the Los Angeles Department of Water and Power. They're the largest system in California and one of the largest in the United States. So in terms of Hong Kong, they would be similar in size, serving a large population. They have organized around the new regulations in California. They have dedicated staff now under a water loss task force. They are still early on in their process, but they are situating themselves to make significant progress in coming years. Unlike Hong Kong, they are spread out over a wide area. So even though they're a large system with a large population, they don't have the density that Hong Kong has. Halifax Water on the Atlantic Ocean in Eastern Canada, much smaller system, but they are coastal also, but they also see a wide variation in elevation. So they have many different pressure zones. They are a leader in leakage management in North America. Their system is fully sectorized with district metered areas where they can measure flow into small discrete areas at the different pressure levels. They are doing some pressure management. So they are a good example for Hong Kong in having established district metered areas throughout their system. Like Hong Kong, they see wide changes in elevation. And I know like Hong Kong, who is establishing district metered areas, they are probably a bit further along in their journey and could serve as a good example for the water supplies department. And I'm sure they'll be happy to share their experiences with the water supplies department. So looking forward in the United States, we're still somewhat early in our journey, at least relative to the United Kingdom and some other countries. But we have drivers occurring similar to everyone in the world: water shortages, scarcity, climate change. Much of the infrastructure is aging and declining. Funding is an issue. How regulatory requirements will shift or change, we don't know. We are trying to embrace new technology as it comes along. And the future, what will it be? I don't know. I don't have a crystal ball. I'm hoping it'll be the first with lower levels of non-revenue water. But I'm realistic enough to know that there will be still struggles in our future. So that's my quick overview of the United States. So I will stop right there.
Okay, thank you very much, George. George and Malcolm, both of you have done an impossible job, okay, summarizing like 30 years history, okay, in 20 minutes presentation. There's a lot of information to be squeezed in, okay, in a 20-minute presentation, and there's a range of experiences, complexities, and awaiting us is an even more challenging job, okay, for our discussants, okay, seated to my right, and because they have to make a connection, okay, between the UK and the US experience and Hong Kong, okay. Now, I'd like to introduce our two discussants. Seated to my right is Mr. Leung, okay, Mr. Leung, Wing Lim. And Mr. Leung is the team leader of the water loss control team with the water supplies department here in Hong Kong. And next to him is Professor Shih, and he teaches in the Department of Civil Engineering. I'll invite Mr. Leung to, it's a challenging job, okay, to make a connection between what has been going on in the US and the UK in the last like 30 years, and what are the lessons that we can sort of draw upon, okay, their experiences for Hong Kong. Yeah. Mr. Leung.
Thank you, Frederick. I would like to respond to Malcolm's presentation first. The Water Supplies Department is the only service provider in Hong Kong. There's no regulator like the offered here. The department sets its own goal as regards the water loss reduction target, but its performance is monitored by, because it's a government department as well, monitored by the Audit Commission, the Ombudsman, the Legislative Council, and also the public. Malcolm, you have tossed around the idea of zero leakage. I must admit that this is a very noble goal, but it is a too stretch a goal for our department, at the present moment, particularly taking into account the resources required to achieve it. I would think that the most rational approach is to deploy resources according to the level, so-called economic level of leakage for individual supply area, which is arrived at by, say, a cost-benefit analysis. But pure rationality is not adequate in the realm of public administration. We understand we have to take care of the expectation and the perception of the public. So we have decided to promulgate a global leakage reduction target to address the public's concern, as well as a demonstration of the department's commitment to support the sustainable development of Hong Kong. The target is by year 2030, we aim to reduce the percentage leakage from the current 15% to below 10%. How do we achieve it? If we do nothing, the network will deteriorate and the leakage will increase. So in year 2000, we launched a 15-year R&R program under which 3,000 kilometers of water mains would be replaced or rehabilitated. After the program, a substantial completion by 2015, the water intelligent network strategy followed. Under the strategy, we divide the whole territory into small, manageable size, ultimately around 2,400 DMA, district metering area, or PMA, personal management area, will be created for the continuous monitoring of the network within this small area. We fully agree that innovation is a key, as mentioned by Malcolm. Such innovative technology will include, say, AI, dynamic hydraulic modeling, advanced leak detection, etc. Essentially, to answer two questions. One, where is the leak? Two, how much is leaking? Despite such rapid advancement in technology, I must say that we should not forget our lowly, humble infrastructure in two particular aspects. One, accurate metering. Two, accurate network configuration. They are necessary for the provide the context for the effective deployment of all this advanced technology. It is at the present moment, if not for the many years to come. I will now turn to George's presentation, particularly about 2 points: performance indicators and reliable data. We have been measuring and assessing various performance indicators and metrics for our internal reference. But for the purpose of communication with the public, we only use the volumetric percentage. I understand that, and George has rightly pointed out the shortcoming of this volumetric indicator. But after taking into account all relevant circumstances, we would still prefer to use this volumetric indicator for the purpose of communication with the public on the following reasons. One, all indicator has some limits or varies. It depends, at the end of the day, is a matter of trade-off, between simplicity on one hand and comprehensiveness on the other. The most important point is to choose the right indicator for the right occasion, for the right purpose. Two, we have been using this volumetric indicator is relevant, simple to be understood by the public, and has been used for many years. The public can also monitor the trend over the years. Third, this indicator is also now widely used by many utilities in the world for benchmarking. Fourth, the true meaning of the per connection indicator relies heavily on a commonly accepted definition of the term connection, which is still lacking at the present moment. Different places mean different thing by the term connection. Reliable data, George has mentioned about the importance of this, the data validity. We can't agree more on this. I would allude that in the context of water loss management, flow data measured by flow meters are the most important data. So we categorize our flow meters into three groups. One is production meter. They are the large volume flow meters measuring flow at the water treatment works and service reservoirs. Any small inaccuracy in these meters will produce error in huge amount of volume in absolute term. So we use electromagnetic flow meter with an accuracy of 0.5%, but we still need a robust calibration program to uphold the credibility of the accuracy of such flow meters. We use so-called in situ volumetric tests for calibrating these large diameter flow meters. The second category is the medium-sized electromagnetic flow meter in our distribution systems located in primarily DMA or PMA. Since there's no nearby reference tank for the in situ volumetric test, we will transport such flow meters to the test bed for volumetric testing, but the in situ characteristic will be lost. But this is the second next best option we can have. The last category is the consumer meter. We have around 3 million of them. They are primarily mechanical ones. They tend to under-register as they age. So we have a meter replacement program in place, driven by factors like volume through age, throughput, and the revenue recovered weighed against the cost of replacement. Thank you.
Okay, thank you, Wing Lim. Yeah, may I invite Professor Shih, Kaimin, please?
Thank you very much. Thank you, Malcolm and George. Wonderful, inspiring presentations. With this two great presentation, I really want to start with something a little bit more philosophical. We talk about water as a limited resource, but if we start to think before we really have the built environment and the water basically running in front of you in the rivers and more than what you need, then what is the value of the water? That becomes a very interesting and probably difficult question to answer. But of course, in a lot of the built environment that we have today, we don't have such a luxury situation. The water becomes somehow a limited resource, but in terms of what value of that water, sometimes we probably need to think it is a management problem. Like what Malcolm mentioned very nicely, can we reach zero leakage? Can we reach zero water loss? Then if we cannot, that means that we will definitely have to have some water be lost. And how much we're talking about, and that is somehow relevant to Wing Lim mentioned about the goal. So I think in a lot of cities, when they look at this water loss problem, they have to think how they set the goal, why they set a certain goal. And I think that has something to do with very important one that Malcolm also mentioned, the asset management. The balance of the situation that you want to get in control together with the benefit that you get will be I would say, a nice balance that you have to strike on. Therefore, in terms of that equation will be balanced by financial factors, or sometimes you may have a strategically important location that you want to reduce the water loss right there, but not the other area. So I think the overall question, when we really look at the two talk that gave us, I think it's an asset management problem. That's a management of different action, different decision. And that's not a simple engineering question to go fix it or not. Second point that I want to also emphasize is that both speakers mentioned about the great technology available for us to use. And I think that technology, I believe, is not only for the engineers to participate in there, because we can see even from the presenting of the data, both of you mentioned about not using percentage, but more on the actual volumetric loss, although by using the percentage, you may also have certain benefit. But what I try to say is that starting from the presenting of the data to all the way that we look at the analysis of the data, even a lot of different detection method, even the way that we repair, not even talking about the logistic management, how fast we can respond to the repair work. All of this are all in different fields of the knowledge, of the skills. So I truly feel that, particularly one of you mentioned that probably a lot of young engineers these days are not necessarily thinking tackling water loss is an innovative engineering practice, something really fancy and attractive. I don't think that is the correct idea, because you are actually looking at a wide varieties of technology that need to be used to address the problem that we're looking at, and that come from very sophisticated, maybe AI or even data mining, and also the wireless technology to have a quick response, etc. I think I can come with a huge list over there. And other than we know those available tools, another things is the decision making. What tools will be useful? We will definitely not have the luxury to make all the tools and try all the technology to any specific sites. However, with the understanding of the tool, with the understanding of technology and sufficient discussion, I think that outcome will be more applicable to the actual situation that you have to resolve. So that's the current situation that we're facing. Let me touch the final part a little bit on what we call forward-looking. If we are just satisfied with the situation right now, I think we probably lost a great opportunity to really tackle certain issue in the early stage, or fix the problem, or prevent the problem to occur. That's why I would encourage people to really look at how can we actually have a relatively more mature and convenient method to prevent the loss incidents. At the same time, of course, or to reduce the current situations if the situation are going to happen. This is because I think the network that we're facing, the nature of the situation that we're looking at is actually dynamic. We have the pipe system keep aging. We have different kinds of the operations. So I think the preventive and more so-called forward-looking strategy should also come into the play in terms of the current situation that we're just trying to look at and try to fix that. I think the possibility over there can have a quite different approach. Some can be very expensive. For example, we all understand the new lane pipe. If you have some so-called fiber optic technologies and to help them, that will be relatively good. There will be, at the, I would say the winning stage at the very beginnings to safeguard the situation. However, I believe there are also other opportunities if you're not going to invest a lot to that. For example, I think all the data in terms of the main burst, or the leakage incidents, have we actually made good use of those incidents to basically take a good look of the reason? There could be many factors to cause the failure and cause the water loss. For example, corrosion, you can have the inside out or outside in corrosion pattern. It might be because of the choice of a raw material. It might be because of the certain workmanships of a certain part. It might be different type of factor from outside affecting that specific location. Have we actually take this opportunity to do, number one, a good recording, a good forensic work, and then with that data to help us to narrow down certain area they might have the repeating situation and help with a much better preparedness, if not also much fast response to the situation that we are expecting it about to occur. So I think that would be probably something that I feel very inspired from what I heard from both of your talk, and thinking about something like we may be able to further talk about. Thank you.
Okay, thank you very much, Kaimin. Yeah, I'm looking at the laptop computer right next to me. There are several questions. In the interest of time, we are now at 7:09. We have 20 minutes. Yeah. Now, Malcolm, there's a question for you. So let me read the question. I'm going to paraphrase the question, okay? Now, in your presentation, okay, you make a reference to a set of like innovations or innovative technologies, including sensors, data communication analysis, advanced leak detection technologies, okay? Now, the question here is this. I think you also mentioned, okay, that there are causes, there are delays, okay, in repairing, okay, the leaks. What are the major causes of those delays, okay, given that you have the technology to detect all these leaking pipes, okay, in terms of location, okay, I mean the sensors. We basically were supposed to give you sort of like immediate, okay, information on where the leaks are. Is it correct? But then the question here is that if there are delays, what are the reasons for the delay? And then is there any way to reduce that delayed time, to repair the leakages?
I don't, if I understand the question correctly, I don't think there are delays in getting the data from the sensors. The sensors, if they're put out across the network, and these are attached to hydrants, valves, meters, pieces of pipe that are exposed, they're continuously monitoring the leaks or the noise. What are they doing is picking up a signature, a noise signature that's anomalous, different to normal. So once you have two sensors, each with a noise, picking up a noise, they can immediately correlate between those two sensors and pinpoint the leak. So I don't think there's a delay. If these sensors are programmed to be working continuously.
The delay referred to the repair work that should have been conducted after the leaks have been identified.
Repair, yeah, the reason for there are many reasons for delays in the repair. I mean, as we spoke about in a recent seminar this week, if in an urban situation where you've got a lot of congestion, a lot of traffic, a lot of people going to work, and there's always a gap, always a delay between getting the official permissions to open up the road or to close the road and then open up the hole. So this is my point about using innovation for increasing the efficiency of repairs, because if you don't have to open up the road to conduct a repair, you make it a lot faster. And between the time between being aware of the leak and fixing it and checking it can be minutes if you have the type of repair technology where you can go inside the pipe and not outside the pipe. So that's the big delay, I think, is getting permissions to open the road and to repair. That's got a cooperation and collaboration between institutions and between public bodies like county councils and traffic and highways people. That's got to become more useful, I think.
I think this problem is particularly pertinent for Hong Kong, okay, because a lot of the pipes, okay, are buried under major highways. And we're just trying, I think the person who asked this question, okay, is trying to find out whether or not, okay, there's some like clever solution or clever solutions, okay, to this particular challenge, to reduce the delay, okay, in repairing leaking pipes, in the UK.
We'd all like to have clever solutions, I think, Frederick, and I think we're coming towards that. I think because I think I mentioned that it's not just innovation; it's collaboration and research. And I think we are now in the UK. We're achieving better collaboration between suppliers, between water companies, and between the regulators. And they're, in fact, as I said, Ofwat is sponsoring an innovation fund. But I think the gap here is, as I see it, is between the contractors who are there to repair the leaks and fix the leaks, and the people responsible for the public roads and infrastructure, not just water pipe infrastructure, but the roads and the traffic management and keeping the traffic flowing. I think that's where the big gap is in time at the moment. And then there's the other gap, of course, when you've fixed the repair and you haven't fixed it properly, and you have to go back and do it again, and that's another problem.
Okay, thank you, Malcolm. Yeah, George, I have a question that is directed at you. Yeah, let me read the question, okay? Now, we understand that many water utilities are still using the percentage indicator, okay, or their own measurements of water losses instead of adopting, okay, the indicators recommended by IWA or AWWA. Yeah. What do you think are the reasons deterring water utilities from adopting more innovative or more useful indicators aside from the volumetric or the percentage indicator? Yeah.
At a broad level, I would say awareness is one issue. Percentage has been around for 60 or more years. The newer methods may still appear to be new to many people, or many systems may not be aware of them. In the explanation from Wing Lim, as he noted in the Hong Kong situation, the definition of what would constitute a connection is a big factor, because I do feel looking at volume per connection is valuable, but across the United States, connection for the most part means a small building, a single family home. That's the most common in the United States. Where in Hong Kong, connection, probably the most common, I might guess, is a very large building that houses thousands, hundreds to thousands of people, maybe. So that's a whole different thing. So I'll admit that is different. But there are indicators that can look at loss volume per kilometer, by length of pipeline. So that might offer an alternative. And I think to a certain degree, I know in the United States, it's slow to move because many of the state and regional regulatory agencies have used percentage, and I'll just call it inertia. They're slow to change, and they, I think, are fearful if we change and we go from one number, I only have to manage one number, that's easy. And now you tell me I have to look at 5, 6, 10 numbers, that's hard, or that will take a lot of my staff time. And in fairness to the agencies, they're short with staff oftentimes, and they see this as a new burden. So I think in some ways they feel it's easy to just stay with the percentage. So I would just suggest to look at the indicators, the other indicators. If you're still using the percentage, okay, but start to trend the other percentages too, because the fear could be that the percentage will not assist you. You may actually achieve loss reduction that the percentage doesn't reveal, and some of these other indicators may actually be more representative and reveal your success in reducing the loss.
Okay, thanks. Here's a question, George. It's a technical question, okay? And that to do with this concept, infrastructure leakage index. Because we have come across data, okay? So in some countries, that number is more than 1, okay? In theory, okay, you should not go under 1, right? So how do we ascertain the level of unavoided loss? And so how could, okay, in some countries, okay, in some cities, okay, the infrastructure leakage index, the value of the ILI is smaller than 1.
So the thinking around the ILI has evolved. The ILI now is a concept that was developed over 20 years ago. I think it's a fundamentally sound concept, but it includes an equation for the unavoidable annual real loss as the denominator. The ILI is a ratio, and that equation has a number of inputs into it. And the derivation of those inputs were based on certain data and assumptions at the time, 20 years ago, on what could be, in theory, a low-level loss. I think now what we've seen in numbers of systems worldwide have achieved leakage below what some of those initial assumptions were. So these are being revisited, and we're seeing now that if you use the original equations, that some systems get below 1, and that could be valid. Now, we have to be cautious in the United States because we also see many systems that report an ILI below 1, and we know the data quality is very crude, and it's an issue because they have poor leakage management, yet they show a low ILI. So that's just a data quality, data error issue. So I think what you'll see, and I know work is occurring right now to refine, and perhaps in the near future of next several years, perhaps there'll be an updated equation for UARL that will recalibrate that equation and maybe bring a 1 back to a representative level.
Okay, well, thank you very much, George. You have resolved a sort of like a mystery, okay, for us when we come across those data where the value of IRI is smaller than 1. Yeah. We have a question for Wing Lim. Yeah. And this question relates to this concept of infrastructure leakage index. The question, okay, actually there are several questions were combined, okay. First of all, do we have the necessary data to calculate the infrastructure leakage index for Hong Kong, okay? Is it possible to keep the percentage indicator, because it's easy for the public to understand, right? At the same time, to develop, okay, or collect data, okay, you get the data, okay, to calculate the infrastructure leakage index for Hong Kong, to benchmark Hong Kong's efficiency, Hong Kong's water system efficiency against other water system, okay, in other parts of the world, which have reported the ILI figures.
Thank you, Frederick. The ILI, as George has just explained, the denominator involves the equation, which involves the number of connections. The connection is problematic here. I would say that we do have comprehensive record on our digital mapping, but we need, first of all, we need to determine the definition of connection. Even in Hong Kong, we still need to determine how to count the number of connections. So a connection can be a fire service connection, potable water connection, or a temporary means water for flushing connection, or for a building, a large building, we may have more than 1 connections per building. So actually, I'm not an expert in GIS. I don't know whether I can use spatial inquiry, you know, to take out such statistics. I'm not sure. But the first question to ask is, what should we use with such information? I will say we have to spend a lot of effort, but if it is useful, then it's maybe worthwhile to take out the information. Then I have attempted to look into the utility of this ILI. I noticed that, you know, it claims to be useful for benchmarking, but I don't really disagree very much because it involves the connection, the term connection in its formulation. So if we don't know there's no commonly accepted definition of connection, how can we use it for benchmarking? That's my first question. And even though if we overcome this definition of connection, I've read some article, I think World Bank, saying that the ILI can be grouped into, say, 4 categories. If for low ILI, it would say that you are doing pretty good. For higher ILI, you may say there's potential for improvement, and even higher ILI, you may be classified as poorly performing, and for very high ILI, you are not performing at all, I think. Yep. And what's complicated issue is it's divided into high income band and low income band. You know, I think in Hong Kong, at least in Hong Kong, we are sophisticated enough. Please permit you, ask me to use this term, not to rely on such information to tell us whether we are doing good enough. We know from the DMA, we know the absolute volume of water. We know the all kinds of you know, per leakage, per kilometer, or per household, or whatever. I think we collect all kinds of indicators. But we are as far as the DMA is concerned, we are more interested in the absolute volume of leakage, the volume of leakage per kilometer, and also the discrepancy between the inlet flow meter and the aggregate of the consumer meters. We use these three key parameters to prioritize our treatment actions for different DMA or PMA. So I think, at least for me, I think I have to convince me of the utility of the IOI before I spend effort to find out the IOI.
Okay, well, thank you very much, Wing Lim. Yeah. There's one more question for you. Yeah. How would you comment on the absolute amount of water loss in Hong Kong? Yeah.
The real loss, I can recall from percentages, 15% for government mains and maybe 8.5% on private mains, the real loss. So our system input volume is around 1,000 million cubic meter. So that works out to be, I think, 2,500. 250 million cubic meter per year. Yeah.
Mm-hmm. Okay, thank you. Yeah. Question. George and Malcolm, would you like to make any last minute remarks? Yeah, we have 4 minutes. Yeah.
I think maybe leave it to the delegates to ask answer the remarks. But no, I have no other question except this connection business. I think that's something that needs to be addressed. Well, what is a connection? I think Mr. Lim Leung, he made a good comment on that. I think in the UK, it's and in the States as well. I think it's always been on a number of households. It's just domestic connections per household. So I think if you have one large connection with 100 household units in it, it's still possible to calculate the number of connections by adding up those household units and not having it as one connection, but having it as 100 connections. I don't really see the difficulty of doing that if you want to change your performance indicator to volume per connection per day. So I think there's an answer. There is a solution to this connection problem. But I agree, it does. I don't think hydrants are necessarily. I don't know what George thinks about that, but I think we're looking at connections in terms of domestic use.
Yeah. Okay. You know what? Our time is running out, so let me conclude. Yeah. First of all, I need to thank. Excuse me. I'd like to thank both Malcolm and George for joining us. Okay, in very remote locations. Okay, Malcolm in the UK and George on the East Coast in the United States. And also like to thank our two discussants, Wing Lim from the Water Supplies Department and Kaimin from the Department of Civil Engineering. Yeah, and I've been for those joining us online, we are actually watching a large TV in front of us. And I see the number of participants, okay, fluctuating between 135 to 147. Right now, 137. Yeah, and so I think it's a good number. Yeah, I don't know how to say it. Yeah, we don't really have an index to measure whether or not it's comparable, okay, to other webinars. But this is the first interdisciplinary webinar that we were organizing, okay, and that number has never dipped below 130, okay, for the last hour and a half. So I'd like to thank those who are joining us online, and we're going to organize hopefully just two more webinars, and we're going to organize seminars, okay, in person, okay, meaning COVID-19 is under control, okay, we can get back to life as normal. Okay, so thank you again, Malcolm, George, Wing Lim, and Kaimin. Okay, and thank you those who are joining us online. So we'll see you again in the near future. Thank you.
Thank you very much. Thank you. Thank you, gentlemen.
Bye.
Bye.